Have you ever looked up at a plane soaring overhead and wondered, why exactly is it shaped like that? Like, why do some wings sweep backward while others sweep forward? Well, today we're going to completely demystify all that aerospace jargon. We're going to break down the actual anatomy of an airplane from the ground up to figure out exactly how and why aircraft are built the way they are. I promise you, by the end of this explainer, you're going to be looking at every airplane out there with the eyes of an aerospace engineer. So here's our flight plan for this explainer. First, the core airplane anatomy. Second, control surfaces in action. Third, reading engineering diagrams. Fourth, when form follows function. And finally, unconventional aircraft configurations. All right, starting right off with Section 1, the core airplane anatomy. Okay, let's dive right in. To really get a grip on how a plane is put together, we need to get our bearings. So I want you to picture yourself sitting inside a plane, facing forward toward the nose. That's exactly how engineers establish the left and right sides of the aircraft. Keep that perspective in your head as we start snapping these major structural pieces together. First up is the fuselage. This is literally the center body of the airplane, the main structural volume. It's where pretty much all the usable space is. It holds the passengers, the cargo, the flight instruments, the fuel, basically anything the designers need to pack in there. And interestingly enough, a ton of conventional aviation terminology actually comes from the French, since they were doing so much of the heavy lifting on flying machines back in the 19th and early 20th century. The word fuselage itself is derived from a French word that means a spindle shape. And hey, while we're on the topic, here's another great French linguistic origin for you, the nacelle. Whenever jet engines or propellers are mounted out on the wings, or really anywhere away from that main fuselage, they get housed in this aerodynamic shroud. That engine housing is technically called a nacelle, and beautifully enough, it translates from French as a small boat. It actually makes it super easy to remember when you just picture these little boats suspended out under the wings, carrying the massive power plants that drive the whole aircraft forward. So when you put all of this together on a standard conventional airplane, you've got that spindle-shaped fuselage right in the middle. Attached to that are the wings, which are, of course, your primary lift-producing components. And you can see those engine nacelles hanging right neatly beneath them. Now, check out the back of the aircraft. Those tail sections are absolutely critical. You have a horizontal stabilizer and a vertical stabilizer. You'll often hear them just called the horizontal and vertical tails, or fins. Their entire job in life is to be sized and positioned perfectly to keep the airplane flying nice and steady. Moving on to Section 2, control surfaces in action. Okay, so we've built the structural skeleton of our airplane. Now it's time to add the muscles. We're moving from the fixed, rigid parts to the hinged control surfaces that actually let the aircraft maneuver and essentially dance through the sky. The key here is understanding the direct cause and effect that each of these hinged surfaces has on flight dynamics. First, think about the ailerons out on the wings. When the left aileron goes down and the right one goes up, lift increases on the left and drops on the right. That causes the whole airplane to roll to the right. Next, we have the elevators, which are usually back on the horizontal tail. They control pitch. If you deflect the elevator downward, you increase lift on the tail. That pulls the tail up, which points the nose of the plane down. And finally, there's the rudder on the vertical tail. This controls yaw, which is just steering the nose of the airplane horizontally to the left or right. Now, it's really important not to confuse those steering control surfaces with flaps. While ailerons, elevators, and rudders are all about steering, flaps have a completely different job. They're hinged surfaces, usually found on the trailing or back edge of the wings, though some planes have them on the front edge too. Their whole purpose is just to increase the total lift force on the airplane when it's needed most, like when you're taking off or coming in for a landing. All right, Section 3, reading engineering diagrams. So we have the skeleton and we have the muscles. But long before any of this hardware ever touches the sky, it has to exist on paper. A total staple of aeronautics is the three-view diagram. Take the classic North American F-86H, a really famous jet fighter from the Korean War era. A three-view configuration layout like that is absolutely crucial during the design process. By showing a front view, a top view, and a side view, it gives the manufacturing teams precise dimensions and aerodynamic shapes. It lets the engineers see exactly how the wings, the fuselage, and those tail stabilizers all relate to each other in three-dimensional space. It is honestly fascinating to see the sheer scale of technological evolution when you compare it against how consistent the fundamental designs actually are. If you compare an internal cutaway of a legendary World War II B-17 bomber directly against a modern, radically shaped Lockheed Martin F-117A stealth fighter, you see something amazing. Despite the massive generational gap and completely different exterior aesthetics, the internal structural packaging remains remarkably similar. You still have your ribs, your spars, and specific internal volumes strictly dedicated to structural strength, payload, and fuel. Which brings us nicely to Section 4, when form follows function.
This right here is the core philosophy of aerospace engineering. Airplane design isn't just some set of rigid rules. It's an ongoing, highly complex exercise in compromise. In aviation, form strictly follows function. Designers configure an aircraft to meet very specific mission requirements. But the catch is, optimizing one performance category almost always means sacrificing another. For instance, if you design a plane for extreme high speeds, you're probably going to get terrible takeoff and landing performance. If you optimize purely for a super sleek aerodynamic shape, it might be an absolute nightmare to actually build structurally. Even something as simple as putting the engines where mechanics can easily reach them might mess up the airflow over the wings. That's exactly why there is literally no single right way to build an airplane, and why they come in such a wild variety of shapes and sizes. Let me give you a perfect example of this constant compromise: swept back versus swept forward wings. Wing sweep is a design trick used to reduce aerodynamic drag when you're flying anywhere near the speed of sound. Now, conventional high-speed aircraft use swept back wings, but aerodynamically speaking, you'd get the exact same drag reduction benefit from a swept forward wing. So why don't we see them everywhere? Well, swept forward wings have this combination of aerodynamic and structural forces that basically cause the wing to violently twist and potentially snap under stress. It's this brilliant aerodynamic idea that for a long time was totally held back by real-world structural limits.
And finally, Section 5, Unconventional Aircraft Configurations. But what happens when the technology actually catches up to the theory? If we move away from those conventional shapes, we can see how really specific engineering goals lead to some radical forms. The Grumman X-29A research aircraft is a perfect illustration of this. It boldly features those tricky swept forward wings we just talked about. So how did they fix the twisting problem? Modern, high-strength composite materials. These composites are rigid enough to stop the wings from twisting off in midair. And there's an awesome secondary benefit too. The juncture where the wing meets the fuselage is pushed much farther back on the plane compared to a standard swept back wing. Moving that juncture backward gets those bulky wings bars out of the middle of the fuselage, giving designers a ton more flexibility for internal packaging and payloads.
You might also notice something unusual about planes like the X-29A. The horizontal stabilizers aren't in the back. They're mounted right up at the front. This setup is called a canard configuration. A canard is simply a horizontal stabilizer mounted ahead of the main wing. And yep, you guessed it, canard is literally just the French word for duck. Now, while you definitely see canards on super agile modern fighters, it is definitely not a new concept. If you trace it all the way back to the very first successful airplane, the 1903 Wright Flyer, that was actually a canard design. Later on, designers moved the tail to the back to create the conventional setup we know today, but the canard has made a massive comeback because it offers some really unique aerodynamic perks.
Speaking of the Wright Flyer, it featured that iconic double-decker wing design, which became known as a biplane. For the first few decades of aviation history, biplanes were absolutely the standard. Why? Well, early building materials were pretty weak, so stacking two wings together with struts and wires gave the plane a lot of much-needed structural strength. But again, form follows function. As material science got better and better, designers realized a single, strong set of wings created way less drag. So, right around 1935, the aerospace world made this massive, rapid transition away from biplanes to the monoplanes that we consider standard today. So we've seen that down here in the atmosphere, configuring an airplane is basically this giant, endless puzzle of compromise. But when we look beyond the atmosphere, out to space vehicles, defining a conventional shape becomes even harder. A spacecraft's shape, size, and layout are completely dictated by its specific mission, which means there are practically as many configurations as there are missions. So I'll leave you with this thought to chew on. If an airplane's form so strictly follows its atmospheric function, as we push further and further into the cosmos with entirely new, unprecedented missions, what incredible, totally unimaginable forms will the space vehicles of tomorrow take? Thanks for joining me on this explainer. Keep looking up and never stop learning.